Students, we have to complete it the portion of this uh, groups. So just let the window. So I just so we I just briefly, very quickly go to the uh, this for the few 1 or 2 weeks. We have to just say that we start the course with the binary operation, and this binary operation is simply, we can say that in the form of this we have a any uh, order order pair. Mm. So I just say that uh, so we just say that the binary operation is we have to take any ordered pair of integers m and n, and there is a uh, there is a associate. Just a minute. I just. So, so I just said that. So it just said that every pair of integers m there as associated is a unique integer m and n. So we may therefore think about like just for a addition as a mapping from z cross z into z, where the image of mn is z cross z is denoted by m plus n. So binary operation is simply, we can say that very quickly, is a uh, as a function s cross s to s, where a and b operated as a star of a b, and means from set of all s cross s of all ordered pair of elements in S into S in this form. So this means we have to just say that image of AB belongs to the S cross S under operation. A star is denoted by A star B. Uh, First of all, binary is simply indicate that the operation takes in two elements of a S and splits out a new element. Also, we are written as a operation star as a function from S cross S to S, which means that we have two things particular. This operation should be a well-defined, means we have a given A, B belongs to Z, there exactly one C belongs to S, such that A star B is equal to C. In other words, the operation is defined for all ordered pairs, and there is no ambiguity in the meaning of a composition of B. So means we can simply say that second thing is we can say that S is closed under under the star for all AB belongs to the S, then A star B is again is a member of a this S. So this means simply we can say that we have a binary operations, and we have to cover up to the, you have already covered up to the some portion of the groups, and up to this is stage is 3 to 4 weeks, and you have to moving up to the uh, uh, permutation is there. Addition of integer, rational number, real number are the operation of a binary set of and any n by n matrix. Real matrices are the binary operation addition and multiplication. And if you take a this set S is a 1, 2, 3, and A star B is equal to A for all A and B are the element of S, then we can say that simply 1 star. So we have a subtraction of a is not a binary operation on Z. And similarly, we have to go to the this star. If we define A B star B is equal to A divides B, and clearly on R this is not a binary operation, because the if B is equal to 0, then the map this is not a well-defined function. So in this case, this clearly is not a binary operation. And we have to just say that if we define a AB into the uh, uh, so we have to just say that if define star by A star B, where C is some larger number than A plus B, is again is not a binary operation, because of this. This is not well defined, because if you take any numbers which is not the same, clearly we have to say that if you take some anything about this, we take a so just we say that into this form. If we take A, B is equal to A, composition B is equal to C, where C is some number larger than A plus B. So if we take A and B is equal to A is equal to 2, B is equal to 3, then A composition B is equal to some number is larger than A plus 2 plus 3 is equal to 5. So we have a more than 5 is the 6, 7, 8, 9, all this. So this is not a unique nest. So it's not a well-defined again. So it's clearly is again is not a binary operation. So now we have to just various example of binary operations. Now we move to the main basic definition of the group, and that means we can say that before the group. So this means we have a simply G is a non-empty set equipped with a binary operation. So we can say that it satisfies the non-empty set G, the system of G with the binary operation is star, or we can say that just any operation star is said to be a group if it satisfies the following axioms. There's a closure property for A, B belongs to the G. We have A star B is the member of a G. Associativity condition is also hold, then we have satisfied this condition. A star B star C is equal to A star B O and then C. And similarly, the existence of identity means find a whole set. There exists one of the element E with the property that E with the property with composition of A is giving A, and left and right operating is again the same result. So we can say that we find in certain elements identity. And the last one is the existence of inverse. For every A belongs to G, there exists an element A inverse belongs to G with the property that A composition A inverse is equal to identity, and A inverse composition A is also identity. If G with the operation this is star satisfy these four properties G1, G2, G3, G4, then we can say that this G is a group under this operation. If we have to just say that, but if additionally if this group has also satisfy the abelian commutativity conditions, A composition B is again the same as a B composition A, for all A, B are the element of a G. If this operation is satisfied, then we can say that the group is a commutative group here, or is an abelian group. We call abelian. Set of integers under addition is an clearly abelian group, because if we take two integers, adding these two integers, we getting the again the some integers. So this means we can sum of two integers is again is an integer. So this is clearly this is closed under the operation of addition. And also any two associativity condition is trivially hold for set of integers. Now we take a 0 is the element of a z, and 0 is the element in this set whole is like this. If we take a 0, take a sum of any other integer is giving the integer itself, either left or right. We have to just say that this means the 0 is the identity of this set, is the additive identity of this set. Similarly, we can say that if we have to, if a is the element integer, then minus a is also integer, then a plus minus a is equal to giving the 0, which is the identity element. So we can say similarly that means this satisfy this both the conditions of all the four conditions of a group, and that means this is clearly is a group under the this binary operation addition. Additional, this also satisfies the commutativity condition. If we take a plus b is some integers a plus b, this is the same as a b plus a integer. So this means integers under addition is satisfy the commutative condition. So this was clearly, this is an abelian group. Another, we have to similarly, we have to take a rational number under addition, real number under addition, and complex number under addition also is a abelian group under the binary operation of a addition. And we can recall this if we take a set of rational number under multiplication is clearly is not a group, because set of rational number under multiplication is closed, is not a problem. One is the element which is identity, so this also associativity condition hold. One is the element of it belongs to Q. One multiplied any element of the Q is giving the number of elements of the Q itself. So it's one is a multiplicative identity. In the case of a Q is a rational number, and but there does not exist inverse, because one zero inverse of a zero does not exist in this case, because in the multiplication we have an inverse only. If a is the element of a, then 1 upon a is the inverse. So 1 that is giving the identity. So this means 0 is the element which is not a identity in this case. Suppose we have to exclude this 0 into the set, and then where we have to cite Z star, Q star, R star, and C star in this form. This Z minus set minus 0, and the set of a non-zero integer, set of a non-zero rational number, and set of non-zero real number, also set of a non-zero complex number. So in this way, we can say that all the element of this rational number under multiplication is satisfy the this all the conditions of all the four conditions or the five conditions of the abelianity is satisfied under multiplication of if Q star set of a non-zero rational number, because or the element of a this is the inverse, and so but this Z star under multiplication is also not a group, because inverse again does not exist for any if M is the element, but 1 upon M is not belongs to the Z star. So in this case, we can say that this Q, R, and C, Q star, R star, and C star are the abelian group under multiplication, but Z star is still again is not a abelian group under the multiplication. Similarly, we can say that for a complex number is also this is satisfy these conditions. Now we just say that why Z under multiplication is not a group, because the inverse of a element does not exist in this case. Now we have to just under a very special case of a multiplication, we just say that matrix of any m by n matrix elements of a real number addition is a under usual matrix addition and matrix multiplication. is they satisfy the conditions of a group. So it is a group under these two under addition. So this stat verify all matrix conditions is satisfied. Zero matrix is the additive identity of this, and minus A is the matrix, and minus A is also the matrix for the same. So this means the inverse of a matrix A is minus A is the inverse of a this. But in general, matrix multiplication under user multiplication is not a group, because the again the same problem. This is if you take a real numbers, then the zero matrix is there, and the inverse of a zero matrix does not exist. So we have to just thinking about in this form, we have to start a new type of a matrix. I take a GLN means a collection of all the matrices which are invertible. So which we have a set of elements are the real. So we have to take all the invertible matrices, and then we have to denote it as this means so all the invertible matrices means the determinant of such a matrix is not equal to 0, and that is a form a under multiplication as a usual multiplication under is form a group. But again, this is not an group is because mathematic multiplication associative. So this is trivial identity element in this clearly mentioned is there. Identity is GLNR. We can say any identity matrix is again determinant of identity matrix not equal to 0. So invertible matrix, if you multiplied any identity matrix to any matrix itself. So this is also hold, and we have to inverse is also clearly we have to calculate determinant is not equal to 0. So now this is clearly is a group, but we call this is a general linear group, but very well known this group is not an abelian, because we have to take a, and for n is equal to any 2 by 2 matrix, I take these two types of a matrix. If we have multiplied from these two is equal to this form, and in this form we have to multiply this. So matrix multiplication in general is not commutative. So we can also say that this matrix, this is a clearly under multiplication, this a special type of a matrix where the collection of all invertible matrices is form an abelian group, is non-abelian group, because of the matrix multiplication is not a commutative. And if we have this is a special case, if we have to just take a determinant 0 in place of 0, we have to collection of all the matrix where determinant of is equal to 1. So these are the examples we have to discuss in the class also. So I just recall this. I just take some one example. This suppose a position b is equal to a square b, and this is a group or not. Clearly, this is a close is not a problem, but this is not associative. Because of this, you have to check this. This is associative only case when a square is equal to 1, and this means a is equal to plus minus 1. So this general this is not a unique. So the associative law does not hold in this case. So this is one of the example you have to just see in the lectures. So all this thing we have a verify that this is clearly not associative. This is not a group. These are some examples where the we discussed in the power set union and power set of not group union, power set of natural number under intersection binary operation is again is not a group, and we have to take some special types of examples which is group. Now Z under multiplication is not group, but we have to take a special types of a group of integers modulo n, and this is importance applications this in computer science and cryptography. So group of integers modulo n under addition or multiplication. So first we define the what is congruent modulo n. If n is greater than 2 be an integer, if xy is the element of a z, and we can say that x is congruent to y under the modulo n, we write xy x congruent to y modulo n. This means n should divide x minus y. If x and y have the same remainder when n is divided by n. So we just say into this form. For example, these are the example we have to correct it. This is the main theorem. which is very important for our group theory point of view. For lectures, if we have a n be integer and x is congruent to y mod n, and that is clearly equivalence relation. Equivalence relation means is a symmetric, reflexive symmetric, and transitivity conditions is satisfied. And the proof is very trivial because x congruent to y is mod n is equivalence relation is reflexive. So n should divide x minus x, so it's not a problem. If n divides x minus y, then n should also divide y minus x. And so symmetric is also hold. And n divides x minus y, and n divides y minus z. So clearly n should divide x minus z. So x and z congruent to z mod n. Satisfy all the three conditions. So this means this clearly is a satisfy all the three condition, means is a clearly is a equivalence relation. And if it's equivalence relation, we can find the equivalence classes of this. So if x is congruent to y mod n, then we have to congruence classes of mod n, especially is a zn, and this is the equivalence class of a 0, equivalence class of a 1, and so on up to the equivalence classes of a n minus 1. So here we just say that this Zn now the collection of all the equivalence classes. X is the element of a Z, and suppose n is equal to 4. So we have this is Z4 is 0, the equivalence class of a 0, 1, 2, and 3. And now we have to show that this equivalence Zn under addition. We have to just say that this are the other example for collecting the equivalence classes. Now we can addition and multiplication of equivalence classes in defined in this form, and under these two operation of addition and under the operation of a multiplication, we try to show that this Zn is a group or not. So under addition of equivalence classes, this is clearly we have a well defined because this Zn is a, in this way we have to clearly share that is a well-defined map. And also this if we this is clearly this is satisfy the all the properties of a group. So binary operation for addition modulo n over the Zn. Zn is a collection of all the equivalence classes under modulo and binary operation is form an abelian group. This is already I prove into the this is important and very important in this the field of a computer science. But this set of integer under multiplication is a node group under multiplication of a modulo n, because one is the element of a Z and is the identity, but 0 has a no inverse under multiplication of a modulo n. Again, equivalence class of a 0 has a no inverse under multiplication of modulo n. So this means this again Zn under multiplication modulo is not a group. So when does the element of Zn has a multiplicative inverse? That is the important thing is this. So if A and B are not both 0 and A, B are relatively prime, if and only if there exists integer x and y, we say that ax plus by is equal to 1. And this answer this when the inverse is exist of a, if A is the element of a n and A is not equal to 0 equivalence class, then A belongs to Z and has an inverse if and only if A and this n are relatively prime. So if we have a collection of this A any element in the set of a Zn, and this A and n is a relatively prime, then the multiplicative inverse of a such a equivalence class is exists. So we just I proof in the lectures in details. You can just find out the proof of this. We have to just say that. So in general, we can define un with the set of all Zn star have an inverse in Z in this thing. Means we have to take all the collection, means we have to take a un is the set of equivalence classes of a non-zero Zn, and x and n are relatively prime, this condition. And this un is under multiplication is form a group. So u4 is the element of the 1 and 3, 1 and 3 both are relatively prime to this u4, and u9 are 1, 2, 3. That's all the equivalence classes which are relatively prime to 9. So except non-zero element of Z. So 1, 2, 3 is not a relatively prime. 4 relative, 6 is not a relative prime. 5 is a relative prime. 7 relative prime, and 8 is a relative prime. So these are the elements of a this set UN which are relatively prime to this. So we say how UN inherent multiplication, but not addition, and the multiplicative identity from Zn, and every element in UN has a multiplicative inverse by the that's result we have to. This means we can say that 2 is a 3 in U5, and inverse of a 7 is 3 in U10. So we have to just say that now very quickly we have to recall all these things. Now we move to the finite group. So group is finite when the number of element in this set G is a finite, and the number of element in this is called the order of the G, and denoted by this is mod of a G or order of a G. So number of element in G is called the, if G is the set is a finite, the group is called as a finite group. If number of element is called the order of the group is there. If a group has infinitely many elements, then G has an infinite group, and an order of a G is equal to infinity. So G is equal to 9, 5, G is equal to 9, then this is a element 9 element and the order 9. And similarly, N is a this, and UN is a finite number. This is a under finite group. Then this is a phi n, order is a phi n. Phi n is a Euler function. So phi 9 is equal to, you have a 6, because 9 is you have n is equal to p is a prime, then phi p is equal to p minus 1 are the number of elements and order of such a group is there. Definitely we can say that phi 9 ka matlab, means of phi 9 is U9. U9 means which are the elements are relatively prime to 9, and 1, 2, 4, 5, 7, 8, all are these 6 elements are relatively prime to 9. So phi and 9 is equal to this. Euler function of this is equal to this form, and we can say that the order of this clearly is satisfied to this form. So now we have some very interesting things about this finite group. We have to discuss all the groups which are infinite previously, but now we try to discuss about the finite groups. That means this is clearly 1 and minus 1 under multiplication is a group, and this is a K4, and this is a 4 element, this group of complex number under multiplication of this clearly. So we just say that 1 and 1 is self-inverse, minus 1 is a self-inverse, 1 I and minus I are inverse of each other. So this means now we have to, this finite group, we have to discuss the finite group. We write all this finite group in one of the tables, and that table we have to call as a Keller tables. Means this row and columns are label of the elements of a G. An entry of a entry in a row G and the column H, then we have to take a composition of this. So we have a like this table, Keller table. Then means we have to say 1 into 1 is equal to additive identity is a 1. So 1 into 1 is equal to 1. So 1 is the inverse of itself. Minus 1 into minus 1 is equal to, again we have giving identity element. So minus 1 is also itself inverse. Now I and minus I giving the 1 to I and minus I are the inverse, and minus I into I is equal to 1. So this means inverse of I is equal to minus I inverse is equal to I. In this table, there, because all the elements of this body of a table are the element of this set. This means this is a closed. We have to take all the compositions in this set. So all the elements are there. Identity element, each row and each column is unique. So this means identity one is only one is appearing in this. So this means this is clearly is a unique identity element and inverse of each element. This clearly is from a group, and we have just mentioned all the finite group in the form of a Keller table. Easily we can identify this by the table. Is a group is abelian also, because we have to take a I composition minus I is equal to 1 and minus I composition I is also 1. So this satisfy the commutativity conditions also. So this means we have to this we take one of the example of a Z5 by the Keller table, and Z5 is under addition modulo 5. This is clearly is a group, and all the elements of this tables are the elements of this set G, and each row and each column there is exactly one identity 0 is present, and element of an inverse is 0 is inverse of itself, 1 is inverse of a 4, 2 is inverse 3, 3 inverse 2, and 4 inverse 1. So 2 and 3 inverse of each other, 1 and 4 are the inverse of each other. So in this way we can say that this is a group, and we have to this is a quaternion group. We have to take 8 elements of the complex. This is plus minus 1, plus minus I, plus minus j, and plus minus k. This group is called the this satisfied by the table. You can easily identify this group is clearly is a Keller table by we can show that this is a group, and this is again is a clearly is a non-abelian group. Because we can say that I composition j is equal to minus ji, so this is equal to k. So I ji is equal to minus k. So this means these are not the same. The commutative condition is not does not hold here. So we can say that this is a is a group, but is not an abelian group. Is there? Some very important example of this group you is a Kalin 4 group. There is a 4 elements, and that's a special property for this group. If you have E, A, B, C, then the condition of A square, B square, C square is identity. If you multiplied A, B, and B, A, that is given the third element. B, C, and C, B is another remaining element is there. So this type of property is called is a group, and this is again is an abelian group, and that abelian group is known as a Kalin 4 group is also is called as a small, that means the 4 elements is group is there. So Klein 4 group, and this is the name is honor of a Flex Kalin. This group is a 4 group, or the we can also denote it as a K4. That means that the 4 elements are there. And now then we have discussed in the lectures is elementary properties of the group. I just recall some of them. Means we show that identity of a whole the set is a unique, inverse of each the element is unique, and inverse of that element itself is again we getting the element of itself. If we take a inverse of a B, that means this is giving the A composition B, whole inverse is a B composition, B inverse composition, A inverse. So these properties, basic properties of a group, we have to discussing. The proof also provided into the lectures. If anybody has a doubt or want to discuss these properties proof, you can contact me either by the email, or you can just by the course page. And also we have to discuss some other properties like cancellation law, both left and right cancellation law hold in the group. If G is a group, AB is equal to BC, then B is equal to C, or CA is equal to B is equal to C. And one more property is the equation. If this means there is have a unique solution, and after that we have to discuss some integral exponents of the elements of a group, and then we have to discuss some of the problems related to this first week. Almost some problems we have to discussing. If you have any difficulty in these problems or doubt, you can just contact me, and we have to provide you the details about and we can discuss anytime you have to in this form. Next, we have to move back. Next week we have to move to the about the subgroups. So GBA group, we take a subset of a G. If H is a subset of a G, and this H itself is from the property of a satisfy all the properties of group, then this H is called is a group. This H is also called a this H is called a subgroup of a this group G. So now we take a set of integer under addition is a subgroup of a set of real number under addition or complex number under addition. Set of real number under addition is a subgroup of a complex number because R is a subset of a C, Z is a subset of a R, Q, C. So Z is a subgroup of a rational number, real number, and the complex number. And we have to this thing similarly. And similarly, if we have to just take a 1 minus 1, I minus I, now we consider a subset H is equal to 1 and minus 1, then H is a subgroup under multiplication is a subset, satisfy all the, this is also satisfy all the properties of a group and clearly is a subset. So we have to just say that. So this means H, there is a two trivial subgroups of each and every group is identity. H is equal to identity is a group, and that is called as a trivial subgroup. And a subgroup is called as a proper if proper subset of a G is called as a, if we take a proper subset of a G is called as a proper subgroup if we have to this. So many example we have to discussing in the lecture to investigate the point subgroups are this thing. So we have to take various example. Now there is a some discuss another. We have to some of the properties, the criteria of a showing that the subgroup. So we take a G as a group and H is a subgroup of a G. If there is only two ports, because we have to take all the satisfy condition, but we remove this is only identity element of H and G are the same, and inverse of a H belongs to H. The inverse of a H belongs to G are the same because we prove that identity element over the set is equal to unique and inverse of the particular element is a unique. So this should be belong to the same set. And then we have to another criteria we can say that we take any non-empty subset H, a subset H of a H of a group G is called a subgroup if H is non-empty, and if we have to close under this operation, whatever the operation of H and G does remain the same, and every if H is the element of H, then H inverse is also the element of H. And after this, we have to provide a proof of this, and we have to prove some examples also in this case. And finally, we have to just say that one more equivalent conditions, prove the equivalent conditions of criteria of a subgroup. Let G be a group and H a subset of a G. Then H is a subgroup if and only if H is a non-empty and XY belongs to the H, then implies that XY inverse is also the element of H. So this types we have to complete the criteria of a subgroup, and we have to prove various theorem of in this lectures of subgroups, provide some examples, some special types of a subgroup means intersection of a any two subgroups is also a subgroup, but union need not be a take a union of a two subgroups need not be a subgroup, but we take a 2Z and 3Z, and they are the clearly the subset of a Z under addition, and means they are clearly is a subgroup bus. But if we take a union, there 2 and 3 are the element of a union, but 5 is not the union, so it's not a clause under the binary operation. So this means clearly in general union is not a subgroup, but we say that the union of two subgroups is a subgroup only if and only if it's one of the set is contained in the other. If H is a subset of a K or K is a subset of a H, then H union K is clearly is a subgroup of this. So we prove this result in the lectures. So and then we have to define the center and show that this center of a group and the center of a group is clearly is a, we provide a center of a group is a subgroup, and then we find the center of a sum. We particularly find the center of a GL2R, and also we have to discuss some other problems related to the subgroups and provide complete solutions. Some of them I provide you into this form. So I think in the first live lectures, I conclude with whatever in the 2 weeks I discuss into this form. If any participants have any questions and doubt, if he can contact me for any times if he have any problems with this. In the next live lecture, we have to cover more um, two more 2 or 3 weeks overview what we have to did into this 3 weeks, and I will be happy to if some of the participants come join this lectures and discuss me the problems. I'm very happy to provide you your feedbacks about the course, how to improve these things, whatever this if you have any lapses, any things about if you feel good to you have to uh, provide me, and so that's the way we can just say that I just clearly if I'm very happy if you have to provide your feedbacks about the course, how to improvement for this course, and I am very happy if you provide me ask me some questions or solutions. I will be happy to provide a solutions. Any doubt you have, I'm very happy to provide clear your doubts on this course. And that's your feedback is very important. So for this first live section, I think this is enough for me. This time is I have to conclude in this form, and I will continue into the next 4 more live sections about the remaining parts of this we have to doing in this course. So I just say that thank you very much for all of you, and thank you very much. So just say that, okay. So now I just stop here. So thank you very much, this thing.